I'm Ray Weil. I'm a soil scientist at the University of Maryland, and you might recognize that name as the author of your textbook. Well, good morning on this beautiful wet morning. I always like a wet morning to go out and look at soils because the soil colors are more intense when they're moist like that on a cloudy day, and soils are beautiful. We like to let them show their beauty. So today we're in what's known as a soil pit. It's a hole in the ground, and at this point in the class we want to get some hands-on experience with soils as they are in the field. So in class we've been talking about all their properties, and this pit has been dug for some time. So one of the first things we need to do when we want to examine a soil and learn about the land that it comprises is to first of all look at where we are in the landscape. I think you can see we're in a wooded area. This is the north part of campus, a little few acres of remnant woods. And if I look around me, I can see that I'm just about the highest point on the landscape. We're near the top of a hill, and I'm looking out on the rooftops of campus, and I can see for many miles to some other hills on the other side of the Patuxent River. So we're on this hill slope. This is a very well-drained position. We don't expect to run into groundwater or anything like that here, but it also will be of interest because of changes that have taken place over a long period of time. You know, the soil, when we dig into the soil, we're digging, it's like opening a book into the landscape, and we're looking at the record of what's gone on here for the last few hundred years and also the last few thousand, and in this case probably for millions of years. So let's get started. So when we approach a soil to look at it through an existing pit, this pit has been here for some time, we usually have to clean it up. If we dig a fresh pit, we'll get a very nice fresh face, but if the pit has been open for some time, the rain will wash the soil down the pit and kind of smear everything together. And when you look at it, you really can't see the horizons that we want to identify. So our first job is going to be to cut a fresh face, expose some nice clean soil that hasn't been smeared, and then you can start to see the true colors. It's getting a little bit redder down here. While we do this is not something you have an assistant do. You do it yourself because you want to be noticing how the soil feels, what the features are as you do it. So it's definitely getting a little tougher to hold my knife in here. This is a fairly stony soil. I'll get to that in a minute, but I think you can see how the colors are richer and brighter once we clean up, especially down here. See how this is covered with that grayer material, and this is actually got some red to it. And once you get down in here, it's actually getting quite hard to dig, and that's because it's got a higher content of clay, which we'll discuss later. So when we get this all cleaned up, we'll start to try to identify the different features. So we've cleaned up a little area of the profile, and we want to go deep enough so that we can see at least down to the B horizon, maybe get past the B horizon, to show you that it is a distinct horizon and doesn't keep going forever that way. One of the first things we want to do is be able to refer to a particular depth. So I've got a little tape measure. Different soil scientists like to use different models. A lot of people say black is the best color because soils don't have very bright colors themselves. But we've got a green one here. Let me turn it over so we've got, I'm big on using the metric system in science. So we want to expose the centimeter side and not the inches side. Okay. So we measure the soil from the top down. So 0 is at the surface. In fact, where we have a thick layer of leaves, those would actually be above, those would be negative numbers in the depth. So what we're trying to do here is be able to identify what type of soil this is, learn how it's functioning, what its features are. And as we learned in class, soils consist of layers called horizons. And these layers, unlike geologic layers, actually form from the surface down. So the rock is weathering down here someplace. In this case, much farther down. But the changes that occur in that geologic material occur from the surface because of the influence of living roots and air and water and heat moving down through the profile. So actually the part that is the most mature, we could say the oldest, although I'm not talking about oldest in years, but oldest in maturity and degree of development, is near the surface. And as we go down through the profile, the soil is less and less changed from the original geologic material. So if we deep dig enough, we get into what's known as the parent material, which is what the geologic forces deposited, in this case, quite a few million years ago. There's some evidence of how long ago this was deposited and what the parent material is, because if we look at this, one of the features that really stand out in this particular soil is that it's got a lot of pebbles in it. Let me pull some of these pebbles out if I can. This one's a little bigger than I thought. So think about these pebbles that I have in my hand. They look brown to you. If I could break one open, they would look a little whiter. Here in the surface where they're cleaner, you can see they're fairly white. And a little bit of brown color, but primarily these are quartz pebbles. And they're here because if I break it open, you can see the white quartz inside. So the brown is a little bit of oxidized iron impurity on the outside, but basically, get a little closer here, let you focus in on that. You can see that it's really the mineral that you learned earlier in the course as quartz. It's very hard. If I had a piece of glass, you would easily scratch the glass. So what else do you notice about these pebbles throughout the profile? They're smooth and rounded, aren't they? There's a whole bunch of them here, and all of them have rounded edges. So you probably know that rounded edges come from rolling around and being ground together, and there's really only two environments in which that happens. One is in a glacier, and we're not in an area that's been glaciated. We're in Maryland. If we were farther north in a glaciated area, we might think that this was glacial till. But since we're in Maryland, that's not a possibility. So the only other possibility is that these pebbles were rocks that had been rolling around in a riverbed for hundreds of thousands or millions of years. So yes, even though we're on the top of the highest hill around, at one time this was a riverbed. These pebbles were obviously deposited by flowing water. So the landscape has changed a lot since this material was deposited, and this is probably over a period of tens of millions of years. This is a Cretaceous area, an area of Cretaceous sediments. We're on the coastal plain of the mid-Atlantic, so we're not too far from the Chesapeake Bay, and this landscape is made of material that washed down out of the mountains into the ancient ocean through these river channels. This was obviously a river here, and has been then uplifted and has been turning into soil for many, probably millions of years. So that's what we started with, was sort of a gravelly river sediment, and then this has been changing into the soil we see today. And it's been changing from the top down, mostly by the action of biology and weather and water. So we can certainly see that things have been added. We can see evidence of that because I've got a handful of leaves. These were added last fall. Every fall, probably for a million years, this organic addition was added to the surface. Plus the trees are always growing new roots and the roots are dying, so there's organic matter being added all the way through the profile. You can see these fine tree feeder roots all the way down, and in fact they would go much deeper than this. So that's one of the things being added to the profile, and because it's mostly added at the surface in the form of leaves and many fine roots. Notice how many fine feeder roots are right near the surface. We'll talk about that a little more later, but even very large trees get most of their nutrients right here at the surface. So this surface layer has actually gotten much darker than the other layer. Now it may not stand out to you, but if we take a sample, let's go ahead and take a sample of this surface layer of soil. put it in my hand. And we can often do an analysis or see what these soils are like much better if we take a sample, and I like to use, it's kind of traditional, to use a 6-place muffin tin that gives us places for 6 different layers or horizons. And this top layer, which is a pretty dark brown color, is the A horizon. It's dark brown because it's been enriched with all the decomposed organic matter, largely roots and leaves and dead bodies of various soil organisms. If we go just a little bit deeper, we're still in an area enriched. It's got a fairly rich brown color to it, but it's definitely lighter than the other. So take a look at these. I think you can see that this has got darker color than that. So when we take samples of this and separate it out, it really makes these differences stand out. Someplace along through here, about where this root is the border of the A horizon. We have an A1 horizon, which is formed since agriculture stopped and the forest took over. And then we have a deeper A horizon, which is probably a relic of when this soil was plowed. And this is probably about how deep it was plowed. Below that, the soil has much less organic matter, and so it's a little bit redder in color, less dark brown. And again, if we put it in our tin, these differences in colors become much more readily seen than they are when they sort of blend together. I think you can see we're going from almost a blackish to a dark brown. This is organic rich. This has got much less organic matter, and it gets its color mostly from the oxidized iron. So we can continue to do this, and while we do it, we want to feel how soft or hard the soil is. So up here, I can easily slide the knife in. Now I'm doing this under wet conditions. The soil is very wet, but still, this is quite soft. It doesn't have much clay. It has mostly sand and silt, and we'll feel that and measure it later. As we get deeper, the clay that was in here has moved down by the process of eluviation. It actually is dispersed, and then it moves down with the rainwater. This is a very slow process, so it takes 5,000 or 10,000 years to get a noticeable movement of clay coming down here. But this top part has lost some of its clay, and it tends to accumulate down here. So we should see a change in color, but also it's much harder to poke my knife in here. It sticks together more. I think you can see it's chunkier, so we'll put that here. Now you can see, I think you can see in the muffin tin that that's a very distinct horizon, right? It's got much bigger chunks, it's much redder, and we'll feel some other properties of it. In the profile, it's a little harder to see that. So you always want to take samples out and put them side by side. Some of the most striking thing to do is to go down near the bottom of the profile. It all looks pretty similar. You know, when the complete novice comes out and looks at it, they think, oh, that's just a brown profile. But when you take this soil and hold it up next to the soil here, you can see that it's quite dramatically different in color and texture and everything else. So this one came from the bottom, and we probably have one more someplace in the middle. Okay. So there's 6 samples to work with. If we look at the depth, the bottom one came from about 105 centimeters, so a little over a meter, almost 4 feet deep. And the next one came from about 75 centimeters, the one above that from about 45, and we had one from about 25, one from about 10 or 12, and then we had the upper 5 centimeters with the real dark stuff. So we've delineated here at least 6 different layers. Now there's some subjectivity to this, but we can actually do this in a systematic way so that you'll get 10 soil scientists, you'll get at least 9 of them to agree after a little discussion. Okay, so it's not as subjective as it might seem. So how do these layers differ? We said that organic matter is accumulated at the top, and that's obvious from the color, and that the clay has been moved out. So the upper layers are likely to have less clay and more organic matter, and as we go down, the reverse is true. There's much less organic matter. It pretty abruptly is reduced here, except in very localized areas. And then the clay begins to accumulate, and you can see it both by color and how it feels. So you remember, at this point, you've undoubtedly learned how to do texturing, how to take a handful of soil and it's moist. You might need a bottle of water to get it a little bit more moist, and how to estimate what the composition of this soil is. So this is one of the things, in addition to color and structure, that we're going to want to describe for each of these layers. So let's just take a moment and review kind of how one goes about determining the texture of a soil. And so far we've identified that there are different layers, and we've been able to, just by feeling it with the knife, we've picked out 6 different layers, starting with number 1 in the top few centimeters and going down to the very bottom of the hole here. So I have a sample from near the bottom of the hole, and this is where the clay is accumulated. So we're pretty sure that that's a BT horizon. We'll explain that in just a second, but in order to determine what's different about these other than the color, which we can see, and we'll do the color with the color book in a second. One of the main things we're looking for here is the texture of the soil and how the texture changes, and the texture being, of course, the proportions of sand, silt, and clay-sized particles. So this sample from the bottom part of the soil is about the highest in clay down here. And to determine the texture, the first thing we have to do is make a nice paste out of the soil, and I've been doing that for a few minutes. So you take a little bit of patience. Sometimes you can do some other things while you do it, but you need to get the moisture just right so that it's a kind of a putty-like material. It takes a lot of squishing around. If there's dry chunks in there, they're going to feel like sand when they're really clay. So chunks of clay will feel like sand unless you get them all smoothed out. So we got it pretty smoothed out now. The way we determine the texture, there's kind of a flow chart we can go through. And for a soil like this, one of the first questions we want to ask is, can you make a ball out of it? Yes, obviously we can make a ball out of it. It's a pretty hard ball. If you can make a ball out of it and it's stable and you can poke it and it doesn't fall apart, then it's definitely not a sand. So if you made a ball out of something that was mostly sand, like 95% sand, and you poked it, it would fall apart. If you can squeeze it into a ribbon, then it's not a sandy loam. So when I say squeeze it into a ribbon, ribboning is the test for the amount of clay, and we get it into a nice putty-like condition, and then we squeeze it across this second knuckle here, across your pointer finger, and we're going to try to squeeze a little bit out at a time. Now this is something that has to be calibrated. Again, you have to think of the universe. Remember, we're in the Maryland coastal plain, so these are very old soils with highly weathered clays. Clay minerals are going to be mostly kaolinite, which is a less sticky kind of clay than you might find in the Midwest and younger soils that have been glaciated, where the clays are mostly 2-to-1 clays like schmectite. So this kind of clay will be less sticky and will be less likely to form along the ribbon. So you have to kind of consider that when you're measuring the length of the ribbon. Just a little bit more water here. If it's too dry, it'll just crumble. We want to make it so it's nice and smooth. And then we're going to kind of pinch out, and working back down, a thin layer of soil. And what we want to see is how long a ribbon can we make before it breaks off. And you can see that it's not getting very long. So this is definitely not a clay. If this was a clay, it would have more than 45% clay in it, and you would be easily able to make a long ribbon more than 2 inches long. This ribbon is breaking at about 1 inch or 1.5 inches, and so it's probably a kind of loam. Okay. And the amount of clay in this is, feels to me, both from the length of the ribbon and from how firm it is, how hard it is to squeeze, it's getting softer as we work it. It seems to me to be in the neighborhood of about 25% clay, but I'm not able to make a very long ribbon out of it. So this came from this zone here, the upper part of the B horizon. So we want to do that to each of these horizons and get an estimate of the percent clay. And for this to be a BT horizon, the T stands for an accumulation of clay, we have to have a 15% increase in the B horizon as compared to the A horizon. So if the A horizon was about 10% clay, how much clay would you need to have in the B horizon before you could call it a BT? You would have to be 11.5%, right, or about 12% clay. So it's not that big an increase, but it's a noticeable increase. So there's no question that this has much more clay in it than this. This is very smooth, not very firm and sticky, and it won't make much of a ribbon. I like to listen to it, because if I hear it grinding, if I can hear grains grinding over each other when I rub it near my ear, then I'm pretty sure it has sand in the name. It could be a loamy sand, it could be a sandy loam, it could be a sandy clay loam, something with sand in the name. So I can hear a little bit of grinding there. So this does not have much clay in it. I can't make a very long ribbon. It has maybe 15% or so. So this is probably a sandy loam, which is a pretty big area. There are a lot of soils that can be sandy loams. But the increase is going from about 15% clay here to a much higher amount. Where did my chunk of clay go? That I was using before. Here it is. It's camouflaged. So this has much more clay than that, but it goes from maybe 15% up to about 25%. So this is a BT horizon down here. So if we start at the surface and do this analysis, we can clearly see a very black horizon. That's the A1. And we can see that second layer, that's an A2, and probably was an AP. And if we see a very even boundary, usually at a depth of about 15 to 20 centimeters, that was an indication that that boundary was artificial, that it was created by plowing. Now if we go below that, we get a zone that has been depleted of clay, because the clay has moved down here, but it hasn't received much organic matter. And in many soils, especially soils that formed under forest, that is an E horizon. It's an eluviated horizon in which things have moved out, and it is not very enriched in organic matter. So you can see the color. It's number 3 here in the pan. It's a little bit lighter than the ones below, less red and less organic matter. This is an E horizon, and it will go down until you start to feel a pickup in the amount of clay, which is about here. So down around here at about 38 centimeters, I start to feel the clay picking up. I can feel that with my knife. So it's easy to stick it in here. It's kind of smooth, and here it's kind of firm. So you can also feel that. I'm making a ribbon. It's holding together and making more of a ribbon there than it is here. Also the color is different. So those are the sort of subtle differences that we're looking for to define where the boundaries are. And then we can start drawing a line. Someplace around here is where the B horizon starts. This is the E horizon. And then we have actually several B horizons that we're going to look at. So to describe these fully, in your lab manual, there's a table which you would use, and it has a place to put most of the information that you want to know that will help you classify and understand the soil. So we usually put the depth first, so we have to decide where these boundaries are. We already said one is about maybe 6 centimeters, the next one is down to around 18 or 19, and then around here around 30 or 33 we're picking up the B horizon, so we can go through the whole profile that way. Obviously it's to change someplace in here where it gets redder. Let's see, about 60 some centimeters. So we put that down on the side. I would put the letters in. You can put them in tentatively. We think the first one is going to be an A1 horizon and an A2 and an E. We've discussed that, and then a BT, possibly a BE. There might be a transitional horizon, but that you really want to fill that out last after you find out the rest of this information. So we already showed you how to do the texture, and the texture ranges from pretty sandy, that's a sandy loam up here, to possibly a loam farther down. We put the texture in, and then we want to look at the structure. So the structure is the way the soil holds together. The texture is the particles that it's made out of. I like to think of that as the sort of the size of the blocks or bricks that a house is made out of, and the structure is the architecture of the house, the rooms and the hallways and that kind of thing. So let's examine the structure a little bit, and we're going to take a closer look down, especially in the B horizon and in the A horizon, to compare the structure. So in the A horizon, the kind of structure we're expecting to find are granules. Now the really black stuff is not the A horizon. You know what this is? We're going to discuss this a little later, but you can see there's a layer of black on top of the soil. It's only 1 centimeter or 2 thick, and it has very little mineral in it. It's almost pure organic matter, and that's the O horizon. And I haven't mentioned it yet because this is so trampled down and sort of washed down that you can't really get a good view of it here. And we'll go to a more undisturbed area. But we can get, to some degree we can see that there's a layer here right on the top. That's some moss growing on it. That's very dark. So that would be an additional layer that I haven't put in the pan. That's the O horizon. So I've only put the 6 mineral horizons in, but there's an organic layer on top. So that would be the first layer, and that's typical of a forested soil. You won't find that in every soil. So the browner material that's just below it is the A horizon, and if we're trying to look at the structure in the A horizon, we take a chunk of soil and gently break it apart, and it will fall apart into its natural structural beds. So you can see that this is breaking into kind of rectangular, fairly angular, sharp. This is a blocky structure. Now it's not very strong blocky structure. It's a little hard to see and it doesn't hold together well. So it's weak. It's medium in size, and it's blocky. And the blocks themselves will break down if you gently crumble them. They will break down into lots of smaller aggregates. So this is aggregate structure. Let me bring this close to the camera. And it's important to realize that almost all of the soil is in some kind of structure. Most of the particles are not out by themselves. So what I have in my hand now that I've broken down the blocks are little aggregates. And if I take the smallest aggregate, I don't know if you can see, say that one. Can you see that one? Okay. You might think that was a particle. let me clear away from that, clean off my finger. I'm going to take my finger and rub it and see what happens. Oh, that wasn't a particle, but it was a aggregate made of lots of particles. It left a little trail. I smeared it and it left a little trail of tiny particles. So the soil particles, except for the sand, which are big enough to see, are too small to see, and they're almost always clumped together and held together in these aggregates. And that's what makes soil behave like soil, because it's not like a solid material or a gel, but it has lots of spaces both within each of these aggregates and between the aggregates. So these are some fine aggregates, but they're pretty strong, and so this has got some fine aggregate structure to it. That's typical of the A horizon. As we go down to where there's more clay in the B horizon, the structure is often larger and stronger, and you can kind of see the way the soil is breaking on these planes of weakness. It's going to break along the natural planes of weakness. I'll bring this over. So these are again blocky beds. They're quite a bit stronger and more obvious than the blocky beds that we saw in the A horizon. They're different sizes, but mostly medium in size. Sometimes they get to be very big. And one of the things we want to look for here in the B horizon that would be evidence that the clay didn't just form down there. Remember, I got this a couple of feet deep, about 50, 60 centimeters deep. We often can see surfaces that are coated with clay. As the clay is moved down through the cracks, it then precipitates out on the surfaces and creates these kind of shiny coatings that we call clay skins or cutans, and I think there's one there. Now they're a little hard to see, but if I move it in the camera, maybe you can see that it's kind of shiny inside here, and there's a clay coating. So these are not real strong, but you can see this coating on there. So it's something that's fairly subtle that you want to look for, but that's a sign of the eluviation, which makes this a BT horizon, which is also higher in clay. So this is structure. Again, it's angular blocky. It's got sharp points to it. This is strong, angular blocky, and it's medium in size. So we fill all of that in, and the horizons may differ. Even if they are the same color, they may differ in texture or structure.